Dear students, in this video on ray optics, we will study thin lenses, image formation, lens formula and power of lenses. So let us begin with the first topic, focus of a lens. You are familiar with it, but we can have a look. See, focus is the point on the principal axis of the lens at which image is formed when the object is kept at infinity. So, you know that the rays coming from infinity are parallel rays, and if we take a convex lens first, you can see this line is principal axis. Now principal axis is the line which joins center of curvature of both the refracting sides. So this is the first refracting side, its center of curvature is here. This is the second refracting side, its center of curvature is here, and when we join this line, this becomes its principal axis. And at the center of the lens, we have an optic center, and a ray passing through optic center does not deviate from its path. Even this ray is passing through the optic center. It is true for thin lenses. Okay, and now you see the rays are coming from infinity, parallel rays, and they are meeting at this point. So a real image is formed at the principal axis. Now a real image is the image formed by actual meeting of the rays. So the rays which are coming from infinity are meeting at this point. So a real image is formed, and if you place a screen here, then this image can be taken on a screen. So a real image is formed by this convex lens when placed in air. And let us look at this concave lens. See here, rays are coming from infinity, so they are parallel, and concave lens is a diverging lens. So after refraction, the rays diverge away, they move away, so they cannot meet here. So what happens is, when you produce them backwards, they appear to be coming from this point F. And you see, if you are watching from here, if your eye is here, you are trying to watch from here, you will feel that the rays are coming from this point on the principal axis. Actually, there are no rays, but our brain thinks it that way only. So this is a virtual image of the object at infinity, and virtual image cannot be taken on screen. If you place a screen here, there are no rays here, so no image will be seen on the screen. So it is a virtual image is formed by a concave lens at its focus. Another important point, see, you know the sign convention, and this is the direction of incident ray. The focus is here, and we measure all the distances from the optic center. So here, look at it, the direction of measuring this focal length is along the direction of incident ray. So focal length is positive. So focal length of a convex lens is positive in air. And look at this one, the optic center will be here. The direction of incident ray is from left to right, and we measure the focal length from optic center to the focal length, which is in opposite direction. So focal length of a concave lens is negative in air. Focal length of a concave lens is negative in air. So you have to remember these points. And now, image formation by a convex lens. You are familiar with it, so nothing new. So first, when the object is placed at infinity. See, this I have just discussed. You can see that a real image is formed When the object is at infinity, the rays are coming parallel to principal axis and they meet at this point F. So real image is formed, and real image is inverted. So the image is formed at focus. It is real and inverted, and it is extremely small in size. But what if the beam is not parallel to principal axis? See, look at it. See, the rays are coming from infinity only, but they are not parallel to principal axis. But then they will meet at a point in the focal plane. So image is not formed at a focus, but it is formed in the focal plane. So here, the position of the image is in focal plane. Nature is real and inverted and extremely small, highly diminished. So when the object is at infinity, the image is formed at the focus. Object is placed nearer to the lens but beyond 2f. So here this object AB is placed beyond 2f. You can see here. Just try to understand this formation first. When the object is placed nearer to the lens and it is beyond 2f. See, we have focus on both the sides. So one focus is this one, f2f, and on this side f and 2f. An object is placed here, and to make image, we can consider one ray which is parallel to the principal axis, and after refraction, by definition of focus, it will pass through the focus. Another ray will take through the optic center. Ray through optic center goes without deviation, and another ray which is coming along the principal axis, this is also passing through the optic center. So this also goes undeviated. So if you look at it, this ray and this ray, they are coming from the head of the object. So head is formed here at the point where they meet, and this ray which is coming from the tail is formed at this point, and in between the rays which will start from here, they will meet here. The rays which will start from here, they will meet here. So full body of the object is replicated here, and image is formed at this point, and this point lies between f and 2f on the other side of the lens. So the image is formed between f and 2f, and it is smaller than the size of the object. Real image is formed because it is formed by actual meeting of the rays. It is real image, and it can be taken on a screen also. So here the position of the image is between f and 2f. As you can see, the nature is real and inverted, and size is smaller than the object. You can see that the rays starting from head meet here, and the rays starting from tail reach here. So it is an inverted image. Now the next situation, when the object is placed at 2f. So here look at it now. The object is placed at 2f. We have f2f on this side, f2f on this side. So take one ray parallel to the principal axis, and after refraction, it has to pass through the focus. Take another ray which passes through the center of through the optic center. It will go without deviation, and we can take a ray along the principal axis. This also will pass without deviation because it is passing through the optic center. And at this point, these two rays are meeting. So image will be formed at this point. You see, the rays which are starting from head meet at this point. So head is formed here. The rays which are starting from tail reaching here. So tail is formed here. And in between, if I take a ray along this direction, it will be reaching here. So the full body of image is formed, and it is formed at 2f. So when the object is at 2f, image is formed at 2f, and they are of same size, and the object is real and inverted. So here you can see that the position of the object is at 2f, nature is real and inverted, and size equal to the size of the object. You can see. Next situation, object is placed between 2f and f. Now what we are doing is we are bringing the object closer to the lens now. So here you can see the object is placed between f and 2f, and by definition, when you take a ray parallel to principal axis, after refraction it will pass through the focus, and the ray through optic center will go straight, and they are meeting at this point, and the ray along the principal axis, this also goes without deviation, and the point at which the rays meet, image is formed. So the rays from head are reaching here, so head is formed here. Rays from tail are reaching here, so tail is formed. So you are getting an inverted image here, inverted image, and the image is formed beyond 2f on the other side of the lens, and it is larger in size. You can compare. So the method of forming image is same. Consider one ray parallel to principal axis and one through the optic center, and you can find out. So position is beyond 2f, nature is real inverted, and size is larger. You can take it on a screen. Now we are bringing it even closer here. So object is placed at f now. Look at it. The object is placed at the focus. See. Look at it. Now object is placed at focus. We will follow the same method. One ray parallel to principal axis, after refraction has to pass through the focus. Another ray through the optic center, which will pass without deviation, and you will find that these two rays are parallel, so they are not meeting anywhere. The parallel rays will meet at infinity. The parallel rays will meet at infinity means we assume that an image is formed at infinity, the rays are meeting at infinity, and a real image is formed at infinity. So, and it will be extremely large. So, the position of image is at infinity when object is placed at focus. Nature will be real, inverted, and extremely large. You will not be able to take that on screen because it is at infinity. Now, object is placed between focus and the lens. Here we have brought the object even closer between the lens and the focus. See? Now, look at it. Focus on the left side f to f, focus on the right side f and to f. The object is between focus and the lens. So you take one ray parallel to principal axis, and by definition it has to pass through the focus. Another ray through optic center, which goes without deviation, and these are diverging rays. So they cannot meet in the front side. So they are not meeting here, diverging. So we produce them in backward direction. So I have produced one ray backward direction, the other one also at backward direction, and if you place your eye here, then you will feel that the rays are coming from something which is placed here. Our brain imagines that way. When you get these diverging rays, our brain imagines that they are coming from this point, but actually there is nothing. So virtual image is formed at this place, you see. And these rays are coming from head, so head is formed here, and this is a tail. And if your eye is like this, your eye can imagine the tail to be here at this point. So image is formed on the same side and it cannot be taken on screen now. So, because it is not formed by actual meeting of rays. So this image is a virtual image. If you're watching from here, the light appears to be coming from this one, say here. So position of image is, it is on the same side, virtual, erect and larger. It is larger than the object. Now, image formation by concave lens, and when the object is at infinity. So when the object is at infinity, you know that image is formed at its focus on the same side. See, image coming from infinity is parallel, and if it is parallel to principal axis, after refraction the rays will diverge, and when you're watching from here, you will feel that the rays are coming from this point. So this point is focus by definition. So the position of image is on the same side at focus. The nature is virtual, erect and extremely small. You cannot take it on a screen. Image formation by a concave lens when object is placed near the lens. So look at it. Now we are placing the object nearer to the lens, object AB. Now by definition, look at it, object, a ray which is coming parallel to principal axis, after refraction will diverge, and when you produce it backwards, it will meet at its focus. That is definition of focus. And now we will take another ray which is passing through the optic center. Look at it. Another ray through the optic center, and it will go without deviation. And then we take a ray along the principal axis, that will also go without deviation. So on this side the rays cannot meet. They are all diverging rays. They are not going to meet on this side. But if you are watching from here, if your eyes are here, you can feel that this ray and this ray, they are coming from this point. So a virtual image will be formed here. So here, if you are trying to watch from here, see, the rays starting from head is this one and this one. So head is formed here, and the ray starting from tail is this one. So tail is formed here. So in this way, a virtual image is formed between the object and the lens, and it is smaller in size. So virtual, erect and smaller. So you can look at it. Position, same side between the focus and the lens, rather between the object and the lens, and it is virtual, erect and smaller. And a concave lens always make virtual images. Using a concave lens, you never get a real image. Now, lens formula for a convex lens. So let us take this. You have already seen this ray formation, image formation. So if you have taken object AB and its image is formed as A dash B dash, and the object distance is U, it is measured from the optic center. Image distance is V, measured from optic center. The focus F, focal length, like this. See, now we are going to find out the lens formula, and you know it is relation between focal length, object distance and image distance. So see what we get. If you look at it here, this triangle ABC and triangle A dash B dash C. See, this angle is 90 degree, this is also 90 degree. These two are vertically opposite angles. So the remaining angle, this one and this one, they are also equal. That means the triangle ABC and A', they are similar triangles. And you know the properties of similar triangles. So I can write A', B' upon this AB is equal to the ratio of the bases of triangles. So A', B' upon AB is equal to CB' upon CB. Look at it. The ratio of perpendiculars A', B' upon AB is equal to ratio of bases CB' upon CB. Right? Similarly, we will get one more pair of similar triangles. So let us look at these triangles now. See here. This triangle MCF and triangle A', this triangle. Now in these two triangles, this angle is 90 degree, this angle is also 90 degree. These two angles are equal, vertically opposite angles. So the remaining angles will also be equal. That means this triangle MCF and triangle A', are similar triangles. And another point to note is that this AB is equal to this MC. So in place of MC, I can write AB also, right? So following the same method, that ratio of their sides, corresponding sides will be equal. So let's see what we do now. So in triangles MCF, this one, and triangle A', the ratio of these perpendiculars A', upon MC is equal to ratio of bases FB' and CF. Okay, so you just look at it. Now you compare this equation and this equation. You can see that this side and this side are equal. See, MC is equal to AB. So we can equate the right sides also. MC is equal to AB, as we have just shown you. So moving ahead here now. Now equating these two, CB' and FB'. Look at it. CB' upon CB is equal to FB' upon CF. Look at it, this one. I have done this one. Now we will write these terms in terms of the known terms. So if you look at it, see, this CB' is going to be equal to this V, and this CB, which is on the other side, will be equal to U. So there is no problem on this side. This CF will be your focal length F. So that is not a problem. Now the problem is this FB'. Now FB', this distance can be written as this whole distance minus this distance. Look at it. I want to find out this FB'. Now this will be the whole distance from here to here minus this distance. So I can write it as CB' minus CF and upon CF. Now we will write all these along with the sign convention, and you are familiar with the sign convention. So this CB' is along the direction of incident ray. So CB' is plus V. CB is opposite to direction of incident ray. So CB is equal to minus U, and CF is along the direction of incident ray. So CF is equal to plus F. So putting all these values in this equation, we will get V upon minus U is equal to CB' is V minus F upon CF is F. So we get this relation. Now cross multiply. Look at it. Cross multiply. You get VF is equal to minus UV plus UF. Take this UV to the left hand side, it becomes positive, and take this VF to the right hand side, it will become negative, and UF is already there. Now divide both the sides by UVF. So what we get? On the left side, this UV and UV cancelled, you are left with 1 upon F. On the right side, UF is cancelled with U and F, and you are left with 1 upon V, and minus VF upon UVF. So VF is cancelled and you are left with only U. So the final lens relation becomes, this is the thin lens formula. The final lens formula is 1 upon F is equal to 1 upon V minus 1 upon U. You are familiar with this relation, and this relation is true for both kinds of lenses. It is true for convex lens as well as concave lens. It is true for virtual images as well as real images. So in here, like I have taken real image, but you can derive the relation for virtual image also, and you can derive the same relation for concave lens also. So the lens formula remains same in all possible situations. Now, linear magnification. Magnification means to magnify, and the linear magnification of a lens is defined as the ratio of size of image to the size of object. So here, the magnification given by a lens, produced by a lens, is size of image HI upon size of object HO, and we are going to find out a relation for it. And as in the previous case, we have seen that, see, those triangles ABC and triangle A dash B dash are similar, and we have already shown you this relation. A dash B dash upon AB is equal to CB dash upon CB. Now A dash B dash is image which is vertically downwards below the principal axis. A dash B dash, it is inverted and below the principal axis, so it is negative minus HI, and the object is above the principal axis, erect, so the size of object HO is positive, and CB dash is plus V, image distance, CB is minus U, object distance, and from here, see this minus and this minus, left and right, they cancelled out. So the relation for magnification by a lens is size of image upon size of object is equal to V upon U. And the relation is same for both types of lenses and for all types of image formation. And see, using the lens formula and this relation, we can arrive at this relation. So magnification in terms of V and F is M is equal to F minus V upon F. Similarly, magnification in terms of U and V, using lens formula and this formula, M is equal to V upon U, you get M is equal to F upon F minus U, and some important information. Now, for a real image, M will always be negative. You see that M is equal to size of image upon size of object, and real image is always inverted, so HI is always negative and HO is always positive. So for real image, magnification is always negative, and for virtual image, image is erect, so HI is positive, HO is also positive, so magnification is positive. Very important point to remember. So for virtual image, magnification is positive, and for real image, magnification is negative. Now power of a lens, let's look at it. It is true for both the lenses. So here, look at it. Now, this image formation is clear to you. Now, if this ray is coming at 1 meter from this optic center. If this distance is 1 meter, let's see. If CD is equal to 1 meter and obviously this distance is focus, and if this angle is theta, then the value of 10 theta will be power of this lens. That is how it is defined. So, power of a lens is its ability to bend a ray of light falling on it. Now, it is equal to the tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optic center. Look at it. This is a light ray which is coming at 1 meter from the optic center parallel to principal axis, and it is converging at this point, and this angle is theta. Then this 10 theta, see the initial path is this one and it is bent through this angle theta, and alternate angles, so this angle also becomes theta. So tangent of this angle theta gives the power of this lens. Supposing it was a concave lens. So if it was a concave lens, the original path is this one and the diverging beam will go along this direction. When you produce it backwards, it will be here at focus. This angle theta and this angle will be theta, corresponding angles. Then tangent of this angle will be its power. So here. So power is tangent of this angle theta, and if you look at this, tangent theta is altitude upon base or perpendicular upon base. Now perpendicular is 1 meter, base is f meter. So power is 1 upon f in meter if focal length is taken in meter, or it is equal to 100 upon f when f is taken in centimeter. Now unit of power is diopter, though it is dimensionless because it is a ratio of distances or it is an angle. So it is dimensionless, but its unit is diopter, represented by capital D, and power of a convex lens is positive and power of a concave lens is negative. So with this, I come to the end of this unit, this video, and we will be taking numerical problems based on them in the coming video. Thank you for watching.